Alright, a two-proportion z-test for significance. So we're just going to dive right into a problem so I can show you an example of this in its entirety. So in January 2010, a survey of 1,415 adults in the U.S., 51% approved of the president's job performance. And in January of 2016, a survey of 1,100 adults in the U.S. showed that 47% approved of the president's job performance. Do these data give convincing evidence at the alpha level of 0.05 of a difference in the population proportions? So to start this out, we'll go ahead and state the null and alternate hypothesis. So if you've done this before and you know what's going on, see if you know what that is. I'd say stop the video and give it a shot. But your null hypothesis is, in this case, null hypothesis is always, we assume, no change. So we're going to go P1 minus P2 equals 0. So no change. And then your alternate hypothesis is P1 minus P2 does not equal 0. So we're going to test that against the fact that there is a change. And we're not really concerned whether it's lower or higher, just that there's not a change. Now we should always also define our variables. We have two of them here. We have P1. P1 is the proportion of U.S. adults who support the president. The president in 2010. Kind of rush along here. P2 equals, put an equal sign there. P2 equals the same thing, proportion of adults. So I'm just going to put quotations. You know, don't do this in your regular test, but I'm just trying to save us time in the video. But it's exact same wording, but it'd be in 2016. So the proportion of U.S. adults who support the president in 2016. There's P1 and P2. The problem already defined our alpha level. Here we would choose an alpha level before we actually perform the test, but it's already done for us. And then, so the next step you need to do is test for conditions. So this is a two-sample z-test, P1 minus P2. So here are the conditions for that. So first off, is it random? Well, the problem does not state that the data was collected randomly. We'll go ahead and make a note of this and proceed with the test anyway. I made this problem up, you know, based on some pseudo correct data from the Gallup poll, but you know, it's a completely made up problem for the purposes of just doing one of these. Next thing you need to check is your independence. It's sometimes called the 10% condition. So you check to make sure your sample is less than 10% of the population. And in this case, you know, both 415 and 1,100 are less than 10% of U.S. adults. And you need to check both populations, or both sample sizes. So once you do that, we can calculate the standard error of the pooled sample proportion. So here's where it gets a little bit different. So what we're going to do, and if I don't have quite enough room, I might have to move some things, but we're going to create this variable called P sub C hat, and this is for the pooled data. And pooled data is simply your successes from 1 plus your successes from 2 divided by your total sample size. So in our case, if you did that, and you're going to wonder where the 722 came from, and I'll show you in just a second. But for the most part, 722 is our successes in the 1415. Whoops, missed the one there. 1,415 population size. And 517 is our successes from the 1,100. And so you add those up, and you would get approximately, and I should put a little approximate symbol, 0.493. So 0.493 is our pooled proportion, or our pooled sample proportion. Then, to calculate our standard error, or our standard deviation of P1 minus P2, P hat 1 minus P hat 2, for our test, it's going to be the square root of our pooled proportion times 1 minus that pooled proportion divided by our first sample. Let me keep continuing this out, plus our pooled proportion again times 1 minus our pooled proportion divided by our second sample size. So in our particular problem, it looks something like this. It is 0.493 times 1 minus 0.493 divided by your N1, which is 1415, plus, same thing, 0.493 times 1 minus 0.493 divided by your pooled proportion, which is 1100. And then you get out your calculator and calculate that thing. Here it is in ti-nspire, so I'll go ahead and add a calculator right here. We've got that in here, and we'll go ahead and calculate that thing. So it's the square root, and we need a fraction plus another fraction. I'm hitting that button there, and then you just put in your numbers. So 0.493 times 1 minus 0.493. I didn't hit a decimal, so I need to scroll back. So 0.493 times 1 minus 0.493 over 1415, and the same thing, 0.493 times 1 minus 0.493 over 1,100, and we got it. So our standard error in this case is about 0.02. So I'll stick that in our write-up. So 0.02 is our standard error, and I didn't recheck my calculations, but that should be right. Large counts conditions is the last thing, or in other words, can we use the normal distribution? And how you check that is you have to check all of your large counts, or all of your counts. So n1 times p hat 1, which in our case is 1415 times 0.51, which was the 722 I was telling you about earlier. And then n1 times p2, don't necessarily need a parentheses, times p2, which is, sorry, that is completely wrong. n1 times 1 minus p1 hat, which is again 1415 for the sample size, times 1 minus 0.51, which is 693. Now here's the thing, is I did some rounding there. You don't ever want to enter the decimals in the calculator because it won't work. So n2, depending on your calculator, times p2, which equals 1100 times 0.47, and you check n2 1 minus p2, p hat 2. Same thing, 1100 times 1 minus 0.47. And in those cases, I ran out of room, but the top one is 517 and the bottom one is 583. And then you just, once you know that they're all bigger than 10, you say something like this: all four are at least 10, so the condition is met. At this point, we're ready to go ahead and enter it into a calculator and perform the test. You could use tables, but I'm going to show both GeoGebra and the ti-nspire. So I'll hit Menu. I'll slide over here to Statistics, and then I'll slide down to Stat Test, and this is a 2 proportion z-test. And it's kind of nice. You just enter the values it gives you, which would be 722 for P1 or P hat 1. That's the number of successes out of 1415. And then your successes for 2 were 517 out of 1,100. We do want this test, the P1 does not equal P2. And you hit OK, and there it is. And you can take a look at our p-value is 0.045. Our test statistic is 2. And so there it is in that calculator. In GeoGebra, you just hit Start GeoGebra, and we're going to go down to Probability. This is geogebra.org. And we're going to go into, instead of Distribution, we're going to go into Statistic, and we're going to pull the drop-down menu, and this is pretty awesome in GeoGebra, I think. At least I think. So this is a z-test for difference of proportions. Down here are your confidence intervals. Here's your chi-squared and goodness of fit. But z-test difference of proportions, I'm going to go ahead and click that, and we want to test that our null hypothesis is 0. We want to test against that it's not equal to 0. Our P1 sample is pretty much the same as entering it into the ti-nspire, is 722 out of 1415. Our successes for P2, 517 out of 1,100. Hopefully I'm typing everything in. You click off of that, move this up, and there you have the same p-value, same z-score. Interesting that the standard error is 0, so I'm assuming there's some rounding issues, or not sure. It just must not be useful in this case for this particular part of it. So we've got that. 2.02 is our standards, or our test statistic. 0.0452 is our p-value, and we're ready to conclude this thing. So we'll go ahead and put our test statistic in the report. Z is equal to 2. Our p-value is 0.0452, and because p-value of 0.0452 is less than alpha of 0.05, we reject the null hypothesis and say that there is convincing evidence of a difference in the population proportion of the President's approval rating from January 2010 to January 2016. You might argue that 0.0452 rounds to 0.05. In this case, it might mean we need to go back and reevaluate the random idea. Maybe this was not random. Maybe we need to go in and take some more samples. So I hope this helps you out, and I will see you next time.